In this video, I'm going to be reviewing the first few topics of differential equations. Starting with number 2, determine whether or not the following expression is a differential equation. For A, this is not a differential equation, since to be a differential equation, you first need to be an equation. Since there is no equal sign, this is not a differential equation. For B, this is a differential equation, as it is an equation, and there is a y prime here. C is not a differential equation. Even though it is an equation, there is no differential equation anywhere in this equation. For D, it is a differential equation since it is an equation, and there are two derivatives. For number 3, it asks to classify the following differential equations as ODE, PDE, linear or nonlinear, and separable or not. If the differential equation is an ODE, also provide its order. So for A, is it an ODE or PDE? It is an ODE since there is only one differential equation here. It is also linear since the y, which is the dependent value, is only in the differential equation. Is it separable now? So for something to be a separable equation, that means the x's and the y's have to be on opposing sides. As you can see, if you move this 10x over to this side, all the x's are on this side, and all you're left with is this dx, which can be multiplied out of this equation, out of this part of the equation, onto this side as well, leaving only the y on this side and all the x's on this side. Therefore, it is also separable. Lastly, since it is an ODE, we have to look at its order. Since there's only one differential equation, we're going to be looking at just that one. We can see that it is raised to the first power, which means it is of the first order. For B, this is only one differential equation inside of the equation, so we're going to be looking at this. Since B is by itself, it's not mentioned anywhere else in the equation, and it is in the differential equation, it is automatically an ODE. Now, is it linear or nonlinear? For just about the same reason, B is by itself, it is in the differential equation, it is linear. And now we have to look, is it separable or not? Well, this dx can be moved to this side, and then this dx can be multiplied to this side, leaving just the db on the left side and all the dx's on the right side, meaning yes, it is separable. Now we look at the order. Since there's only one differential equation, that's all we have to look at, and it is being raised to the first power, meaning it is raised to the first order. Now we look at C. Since there are two differential equations in the equation, we're going to be looking at these. Now, is it an ODE or a PDE? We can tell it is a PDE since this symbol is trying to be derived twice, which is not allowed in an ODE, meaning it is a PDE. Now, is this a linear or nonlinear equation? Well, if we look at these symbols, they're only used in the differential equations in this equation, and they are being raised by a legal power of 2, meaning that they are linear. Now we look to see if it is separable or not. We can do this easily by setting these equal to each other, throwing out a minus sign in front of one of them, as one of them will be moving across the equal sign, switching its positive or negative sign. We can disregard the constant, and now we have this. We can cross multiply each of these parts, And after we cross multiply, we can clearly see that it is not separable. We cannot get both of the top equations on the same side without having one of these contaminating it. So looking at both differential equations, we can see that they are being raised to the power of 2, meaning that it is of the second order. Now we're going to look at part D. An easier way to look at this would be to put this as dy over dx with 2's right here and right here, plus x times dy over dx, just like that. Now, is this an ODE or a PDE? Well, it is an ODE because we need to look at the dependent variable, which is y. Since y is being derived twice, but being derived by the same x, it is an ODE. If they were being derived by two different things, like c, where we have a t and an x here, it would have been a PDE. However, since it's not, it is an ODE. Now we look to see if it is linear or nonlinear. To do this, we simply look at all the times the y is used and make sure it is by itself, not inside of anything. So for this y is all by itself, meaning it is all good. This y is being multiplied by a constant x. That's still all good. This y is all by itself, meaning it is all good, and this equation is linear. If y were to be inside of this sign, for example, it would be nonlinear, since the y value is inside of something. Now, we look to see if it is separable or not separable. This we cannot actually do, because we need to get d of x, we need to get all the x's on one side. That means these d of x's have to go on the other side. To do this normally, we would multiply the whole thing by dx. However, we can see that if we do that, there is a leftover d of x in here and a d2y here, which kind of ruins the equation. And since it ruins the equation, it's illegal, and we can't tell if it is separable or not separable. Now we look at the order. We look at the highest order, this being 2 right here, so it is of the second order. Now we're going to look at part E. So for this, it is easier to write it as d3 of x over dy3 plus 4yt times d of x over dy. Now we look to see if it is ODE or PDE. For this, we're going to look at the dependent variables, that being x. Since it is being derived by y, and only y, both times, it is an ODE. If it was being derived by two separate things, as in c, it would be a PDE. Since it is not, it is an ODE. Now we are going to see if this is linear or non-linear. Since x is by itself right here, it is all good. X is being multiplied by a constant right here. However, that still means it is all good. Since it is not inside of anything, this means this equation is linear. Now, is it separable or not separable? Well, we can't actually tell for the same reason that was of D, because if we multiply each side by dy in attempts to remove this dy and bring it to this side, well, we still have a d3x over dy3, or a d2x over dy3, which doesn't make any sense. Therefore, we can't really state that. But we can tell the order. We look at the highest order, this being of 3, therefore this is of the third order. Now we're going to be looking at part F. There's only one differential equation here, that being w, so we can write this as dw over dx. Now, is it an ODE or a PDE? For this, we only have to look at this differential equation. And since it is being derived by x and only x, it is an ODE. Now we look to see if it is linear or nonlinear. I said before that it has to be outside by itself for it to be linear. However, there is another more correct definition, and that is that linear differential equations are derivatives and functions that occur as polynomials, only being raised to the nth degree. The fact that this is being raised to the first degree is good. However, since it is being multiplied by this w right here, this actually contaminates it, meaning it is non-linear. So again, for it to be linear, it has to be by itself, meaning not inside of something, and it has to be raised to the nth degree. We can also see if this is separable or not separable. To do this, we can do the trick by setting these equal to each other, since there are no other parts of the equation other than this constant 0, throwing a negative sign out in front of one of them, multiplying both sides by d of x, and we see that this cancels out. There's a dx over here, all the x's are over here, all the w's are over here, meaning it is separable. Now to look at its order. Since it is only one differential equation in this entire equation, we only look at this one part. It is of the first order. Now we look at g. Circling the only differential equation in here, we can see that it is an ODE, since the dependent y is only being derived once by x. Now, is it linear or nonlinear? For this, we look to y, and that is all of the y's. We can see that y right here is by itself, not inside of anything or touching anything. We can see right here y is by itself, only being multiplied by a constant negative 1 over x. This y, however, is inside of an e raised to the power of y of x. It is inside of e. Now we look to see if it is linear or nonlinear. For this, we look at the y's. Right here, y is by itself only being multiplied by a constant negative 1 over x. Right here, y is inside of something. It is inside of e, meaning it is nonlinear. Now we can see if this is separable or not separable. For this, I am not 100% sure why it is neither separable or non-separable. My best guess is this e to the x is kind of funky and is messing with this whole equation, meaning we cannot tell what this is. But what I do know for certain is that this is of the first order. For h, this is the differential equation we need to look at. D of x is the dependent variable being derived by d of t. Since d of x is only being derived by dt, it is an ODE. Now, is this linear or nonlinear? For this, we need to look at the dependent variable x. Both times it is neither inside nor touching another x, meaning it is linear. Now, is this separable or non-separable? Again, we cannot tell because of this funkiness inside of e, which is t. What we can tell is the order though, and it is of the first order. For part I, we look at this d of y, which is really d of x over d of y, because it is 1 over d of y over d of x. And when you multiply that, flipping it to the top, you flip it over to be dx over d of y. Since this is the only differential equation in this equation, it becomes an ODE. Now, is it linear or nonlinear? For this, we look at the dependent variable, which would be y. Remember, because this is being derived, this y is being focused on, so it is the derivative of y. However, this y is not touching anything, nor is it inside of anything. It is a polynomial raised to the nth power and the nth power only, meaning it is linear. Now, for is this separable or not, what we can do is forget about this constant, set these equal, put a minus sign out in front of one of them, and we can see that if we bring this x over here with cross multiplication, and we bring this y over here with cross multiplication, we have x times d of x is equal to negative d of y. X is all on the left side, y is all on the right side, meaning this is separable. Now looking back at the derivative, we can see it is of the first order. And lastly, J, we have two differential equations in here. Now, is this an ODE or a PDE? There is this dependent Greek letter. It is being derived by two separate things. This means it is a PDE. If it was being derived by t and t squared, it would be an ODE. Or x and x squared, it would be an ODE. It would be an ODE. However, since they are being derived by two separate things, it is a PDE. Now, is this linear or nonlinear? For this, we have to look at this symbol, since it is the dependent. So these are the three places we need to look at. It is by itself here, and multiplied by a constant here. That is okay, and it is linear. We cannot tell if this is separable or not separable. And that is because of these funky derivatives. They're both being derived by separate things, and they just cannot, we cannot do anything with them. But we cannot say for sure if it is separable or not separable. So it gets a squiggly line. Now, is this of the first or second order? Looking back at the differential equations, we can see what order this is. 2 is the highest, so it is of the second order. For part 4, determine whether the function f of x is equal to x squared plus 1 is a solution to each of the following differential equations. Looking at part A, and looking back at f of x, we need to derive f of x twice. So the first derivative of f of x is equal to 2x, with the second derivative equaling to 2. So the second derivative here says it's equal to 0. That is obviously false. So A is not a solution. B is a solution, and we proved that just now. For C, what we have to do is take the second derivative and add it to the first derivative. We can see that obviously does not equal 1, meaning that is not a solution either. For this, we have x times the second derivative, so that means that would be 2x, and that is set equal to the first derivative, which is equal to 2x, meaning this is a solution. So the only solutions here are B and D. Number 5, consider the differential equation y prime cubed plus 4y minus 4 equals 0. Is yx equals 1 a solution? Is yx equal 1 plus x squared a solution? How about yx equal 1 minus x squared? So if we take the derivative of this, you can see it equals 0. Plugging this back into the original equation, we're going to get 0 plus 4 times 1, because we have to use this y, minus 4 equal to 0. This does equal 0, so this is a solution. We are going to take the derivative of this. Seeing that it is 2x, we can plug this back into the original equation, which will yield us 8x cubed plus 4 plus 4x squared minus 4 set equal to 0. We can cancel these 4's out just like this. We can divide everything by 4. We can also divide everything by x squared. We can see that we're going to be left with a 2x equal to 0. The only way for this solution to be true is if x equals 0. So we can write true if x equals 0. Now we look at this last part. Y of x is equal to 1 minus x squared. Taking the derivative of this, we get y prime is equal to negative 2x. Plugging this back into the original equation, we get negative 8x cubed plus 4 minus 4x squared. Again, because this is our y right here, we have to plug this, all of this, this part, 1 minus x squared, we have to plug this into this y right here. That means there's going to be a 4 out front, and we have to distribute this in. We also have another minus 4, and we can set that equal to 0. Cancel out the 4's, divide everything by negative 4, divide, which will leave us a 2 right here, divide everything by x squared, and this will just leave us 1. So what we're going to get is 2x equals 0, which is exactly the same as what we got in the last problem right here. So holds true that it is true. It is a solution if and only if x equals 0. For number 7, we're asked to consider the function f of t is equal to c1 e raised to the negative 4t plus c2 e raised to the 3t minus 1/10 et e raised to the power of t minus 1/6 e raised to t plus 1/12. Consider the function f of t is equal to c1 e negative 4t plus c2 e 3t minus 1 divided by 10 et minus 1/6 e 2t plus 1/12, which is a family of solutions for the differential equation y double prime plus y prime minus 12y equal et plus e2t minus 1. Find a solution to this differential equation which satisfies the initial conditions y is equal to 0, or y of 0 is equal to 1, and y prime of 0 is equal to 1. We're going to use this part and this part first together. So t is 0. What we can do with this is plug this into this equation. So f of t, or of f of 0 actually, is equal to c1 times e negative 4 times 0. Anything, since this is multiplied by 0, anything to the power of 0 is just going to equal 1. Therefore, this is just c1. Same thing with c2. So we're just left with c2. Same thing with negative 1 over 10. Same thing with negative 1 over 6. And same thing with 1 over 12, but since it's just a constant. And with 1 over 12, since it's just a constant, we're just going to leave it as is. Remember, f of 0 is equal to 1 from this equation right here. Rewriting this, we get 1 minus, or 1 plus 1 over 10, because we're going to move all of these constants over to the left side. So they have to change signs. And that's going to be equal to c1 plus c2, just like this. Writing this as f prime t, we can set this equal to, so I'll bring that out of the chain rule. This is what we're going to be left with. Now I'm going to use the chain rule for the rest of the derivative. So this is what we get when we derive everything. We get negative 4 c1 e negative 4t plus 3 c2 e 3t minus 1 divided by 10 et minus 1 over 3 e2t plus 0. Now what we can do is use this equation to plug into this equation. So this part is equal to 3, and all of the t's are going to be 0. So if this t right here is 0, this t also is 0, and this t also is 0, so all these t's are going to be replaced with 0. Remember, anything to the 0 power is just 1, so this e is gone, this e is gone, and all the e's are gone. Not gone, but they just become 1, so we don't need to include them in our equation. This got a little messy, so we can rewrite this just like this. This is what we have now. Now, we can put all these on one side. All of these that don't have c's are going to go over here. But what we can do is plug them into our calculator and put them all together. To keep it clean, we'll leave it as a fraction. We'll write it as 103 divided by 30 is equal to negative 4 c1 plus 3 c2. We can do the same thing for this top part. by adding all of this side together, all of the left side, adding all the left side together, we can set it equal to C1 plus C2. We can also do this for the last equation, this one right here, and set it equal to C1 plus C2, putting that into our calculator. So you're left with this and this. Super similar. What we're going to do with this part is choose either C1 or C2, and we are going to set that equal to 71 over 60 minus C1 or C2. For simplicity, we'll just write it as negative C1 is equal to C2. 71 over 60 minus C1 is equal to C2. Plugging this function into this function, we get 103 over 30 is equal to negative 4 C1 plus 71 over 30 minus 3 C1. And the way we got this is because we took our C2, we took this, which is C2, we put it into this C2, and we distributed the 3 through it. That should be a 20. So we take this C2 and we distribute it, or we substitute it into this other C2, and then we distribute the 3 into that. Getting this, we can solve for C1. We can bring this over here, and then we can add the C1s together. Doing this, we get 7 over 60 equals negative 7 over C1. Now here, we divide both sides by negative 7, which leaves us with a 1 over 60 is equal to C1. And that is almost part of the answer. So now we have to plug C1 back into this equation to get C2. Doing that over here, we get 71 over 60 is equal to 1 over 60 plus C2. Moving this over here and giving it a negative sign, since we are moving it across the equal sign, we get 70 over 60, or 7 over 6 is equal to C2. We are not done yet, because this problem asks us to find a solution to the differential equation. We need to take this original function f of t and we need to sub in our c's. So we're going to have f of t. So this is what we're going to get once we plug our c1 and c2 in. Remember, our c1 is 1 over 60 and our c2 is 7 over 6. So all we're going to do is plug that into c1 and c2 of the original equation, and we're done. For part 8, we're asked to solve the following differential equations. We're going to do a first, and we are going to separate these in dy and dx respectively. An easy separation technique is to set these equal. Since there's nothing on this side, there's nothing over here, set these equal and throw a negative sign in front of one of them. For simplicity, we're going to do it in front of this one. Now we're going to divide this right side by y squared to get rid of the y squared, and we're going to we're going to multiply the left side by dx to get rid of the dx. Doing this, we get 1 over y squared dy is equal to negative sine of x dx. Next, we can integrate both sides. After integrating both sides, we get negative 1 over y is equal to cosine of x plus c. Now we need to solve for y. So what we're going to do is divide both sides by cosine of x plus c, and then we are going to multiply both sides by y. So we're doing sort of a cross multiplication here. Looking at b, we're going to do the same thing. After separating both sides, this is what we're left with. Y dy is equal to x squared divided by 1 plus x cubed dx. From here, we are going to integrate both sides. Once we integrate the left side, we're left with y squared divided by 2. On the right side, we're going to have to make a u substitution. Setting u equal to 1 plus x cubed, we can use that to finish the integration. After we integrate this, we're left with 1 over 3 u du. How we got this is plugging du over 3x squared into dx. The x squareds cancel out, and we're left with 1 over 3. Remember, we substituted in u for 1 plus x cubed earlier, so that's why that's there. So after this, we need to still differentiate the right-hand side. We're going to be left with y squared is equal to 2 on the left side. On the right side, we're going to have 1 over 3 times ln of u. Remember that u is equal to 1 plus x cubed, which we have to sub back in since we did not start with u. And then whenever we integrate, we always have to have a plus c if we do not have bounds. Doing this, we can multiply everything by 2 and then square root the entire right-hand side to get rid of the squared on the left side. So our final answer is y equals the square root of 2/3 times ln of 1 plus x cubed in absolute values plus c. The reason why it has to be in absolute values is because x to the cubed can be a negative, but ln cannot have a negative inside of it. The reason why it's not 2c is that a constant times a constant is always just going to be a constant. That's it for 8. For number 9, we're asked to find the solution to the given initial value problem. For a, we have y prime is equal to 1 minus 2x y squared. And the value that we have is y0 is equal to negative 1/6. Expanding this, we can see that we have dy dx equals to 1 minus 2x y squared. We're going to use separable equations to get these two by themselves. After using separable equations, we can see that we have dy over y squared is equal to 1 minus 2x dx. After using separable equations, we can see that we have dy over y squared is equal to 1 minus 2x d of x. Now we take the integral of both sides. After taking the integral of both sides, we get 1 over negative y equal to x minus x squared. After taking the integral of both sides, we have 1 over negative y is equal to x minus x squared plus c. Now we can plug in our x and y values. Plugging in negative 1/6 for y, we get 6 on the left side, and plugging in 0 for x, we get c on the right side. So that means c is equal to 6. Since it's asking us to find the solution, what we have to do is take this part, which we found right here, and set up y properly, which would look like this. After we divide both sides by x squared minus x minus c, and we multiply both sides by y, we can plug in our c, which is 6, and we get x squared minus x minus 6 is equal to y. For b, we're also going to use separable equations. However, we need to take care of this e. When anything is in e and it's a plus or a minus, we can break it up to be et times ey. If it's a minus, it would be divided by ey. Breaking this up using separable equations, we get this. We get dy over ey is equal to et dt. Now we take the integral of both sides. After integrating both sides, we get negative e negative y is equal to et plus c. Solving for y, we multiply both sides by ln. Y is equal to negative ln absolute value negative et minus c absolute value. And to solve for c, we can use this equation up here. After we multiply the negative on both sides. So what's going to happen is y is equal to 0 and t is equal to 0. Putting these 0 exponents on the e makes them both 1. So this is just going to be 1 equals 1 plus c. However, on the left side, there is a negative sign, like this. So c is going to be negative 2. After we plug this into our final equation, we get y is equal to negative ln 2 minus et. Number 10 is asking us to solve the differential equation y prime equals x squared over y, giving the solution in both implicit and explicit form. Implicit means a basic solution, basically. It's super basic and it's super easy to get to. Explicit is y completely by itself, super clean solution. To solve this problem, we're going to be using separable equations. So dy in reality, or y prime in reality, is dy over dx. After separating both the x's and the y on their respective sides, we can take the integral of both sides. From here, we get this. We get y squared over 2 is equal to x cubed divided by 3 plus c. This is the implicit solution. Now to get the explicit solution, we just continue solving the problem. We're going to multiply 2 on both sides and then square root it to get the y all by itself. So after we do that, we are left with y is equal to plus or minus the square root of 2/3 times x squared plus c. The reason why there is no 2 times c is because anything times a constant is just a constant. The reason why there is a plus or minus out front is because that is a rule when we take the square root of both sides. This would be the explicit solution. Number 11, we're asked to find a solution to the initial value problem y prime is equal to 3x squared minus ex divided by 2y minus 5 with conditions y of 0 is equal to 1. We're also asked to provide the solution in implicit and explicit form. To do this, we're going to use separable equations. If we recall from earlier, y prime is really just dy over dx. Using this knowledge, we can separate the y and the x's on both sides, multiplying both sides by 2y minus 5 and both sides by dx. After we do this, we're left with 2y minus 5 dy on the left side and 3x squared minus ex dx on the right side. Now we take the integral of both sides. After doing this, we're left with y squared minus 5y is equal to x cubed minus ex plus c. Now we need to find c for both implicit and explicit form. So x is equal to 0. What we're going to do is put an x in here. That's going to become 0. This is just going to become 1. And then these both are going to become 1. So this is going to be 1, and this is going to be 1. I rewrote it so it's easier to see. So doing a little bit of math, we can see that c is going to be equal to -3. Plugging this back in to our equation, this would be our implicit solution. Y squared minus 5y is equal to x cubed minus ex minus 3. This is implicit because y is not completely solved for. However, we will need to do that for our explicit form. To find how we would write it explicitly, now to solve this explicitly, we're going to have to do a little trick. To solve for explicit, we're going to have to complete the square here. We have y squared minus 5y, but that doesn't really help. We have to get y by itself. How are we supposed to do that? Well, we can do this by easily adding a 25 right here, right? But that still doesn't help us because when we take the square of that, we get this, right? That's kind of what we're thinking. However, this middle portion, instead of being -5y, it'd be -10y. So what we're going to have to do is force this right here to be a 5y. How we can do that is by putting a 2 under it. We can divide it by 2. So this is what it's going to equal after if we were to factor out the square. We get y squared minus 5 over 2 minus 5 over 2, which is -10 over 2, which is equal to -5, plus 25 over 4. To solve for y, we need to complete the square on the left side. By doing this, we'll get y squared minus 5y plus 25 over 4 is equal to x cubed minus e to the x minus 3. Since we have a 25 over 4 on the left side, we have to add a 25 over 4 on the right side. This 25 over 4 is just coming from thin air. We are able to do this. We need to do this to get this left side into this form. That way we only have one y on the left side. So this would become x cubed minus e to the x minus 13 over 4. The reason why this is 13 over 4 is because we multiply both the numerator and the denominator of negative 3 by 4, which yields negative 12 over 4. And when we add that to 25 over 4, we get 13 over 4. That should be a positive. Now we're going to square root both sides to get rid of the squared over the y. And then we're going to add a 5 over 2 to both sides to get y by itself. So after we do everything, we are going to get y is equal to the plus or minus of the square root of x cubed minus ex plus 13 over 4. And then outside of the square root, we're going to have a plus 5 over 2. And that is our explicit solution. Number 12 asks us, for each of the following differential equations, determine whether or not the existence and uniqueness of a solution at the given points is guaranteed by the theorem discussed in class. Now, to do this, we're going to have y prime be equal to f of x comma y. We're going to set that equal to this. Now, we're going to multiply both sides by d over dx to get y by itself. Now that we have this written down, we can solve this. So d of f over d of y is equal to x over y. So this is what we're going to look at for plugging these points in. So does it have a unique solution at 1, 1? Well, the answer is yes. 1, 1 is just 1 over 1, which equals 1, which exists. Now, we also have 1 over 0. Since 0 is in the y position, 0 goes to y. This does not exist since 1 over 0 is not valid. We also have to test the original equation, this right here. What we're going to do is, instead of plugging in both points, both of these, into here, we could simply say that everything here exists as long as y is greater than or equal to 0. We can say that y is greater than 0. So as long as y is greater than 0, this will be fine. Now we're going to look at y. We have our y as 1 and y as 0. Plugging in y here, we can see that y is greater than 0. But plugging in the second one, we see that y is not greater than 0. Therefore, only y, comma 1 is for sure a unique solution. For 1, 0, a unique solution is not guaranteed. We're done with that one. Now we're going to look at b. Same thing here. We're going to have f x comma y is equal to x minus 1 over y. Now, to get the next derivative, we're going to have it divided by, we're going to differentiate both sides with respect to dy. Doing this yields us this function. We can take out the y's, factor out the y's on top, and then take out a y from the bottom, and we are left with this. Now we have 1 negative x plus 1 on the top, and we can combine that further to be 2 minus x over y. So we will be plugging in, we will be looking at this part and this part. So plugging in points to where we just found, if we plug in 0, 1, we have to look at, for both of these actually, y has to be greater than 0. Or it can be less than 0. It just cannot be 0. So when we plug in y, or when we plug in the first equation, y is 1, it's totally fine. However, when we plug in the second equation, or when we plug in the second set of points, we have the 0 here. Y is 0. That means the denominator is 0, and we cannot have the denominator be 0. So the only unique solution is at 0, 1. And we are not guaranteed a solution at 1, 0. It's important to keep in mind that although we cannot prove that this second set of points is unique or has existence, we cannot disprove it either. So that is very important to keep in mind. And that is how you would write it. So for this one, we would write the function x, ln y is continuous as long as y is greater than 0. And since x has nothing to do with this, it interferes not. It is continuous for all x. We have a similar statement here for number 12, which is x ln y is continuous as long as y does not equal 0 and is continuous for all values of x. Number 13 asks us to find a family of solutions for 1 plus ex cosine y dy dx equals to ex over y. Then find a solution to the initial value problem y of 0 is equal to pi over 2. So these are our points that we're going to test x and y when we finish integrating this first given equation. Given this equation, we are going to separate it first. We want the d of y and the d of x's on opposite sides so that we can integrate it. From here, after we move everything, we separate everything, we have cosine of y times y d of y is equal to e of x over 1 plus e of x times d of x. Now we're going to integrate both sides so that we can get y by itself. To solve this, we are going to have to do it separately because these are some pretty big integrals, at least the left side is. So for the left side, I am going to use green. And we are going to have to split this. So we are going to do integration by parts. So what this looks like when we're done, we're going to have a uv minus the integral of v du. And the way we're going to set this up is u is equal to y du is equal to dy. You want to take the thing that can easiestly be kind of cut down. You want to have less work for yourself, so d of y is pretty simple. And also, if you just use cosine of y for and for u, you're just going to get a negative sign of y, and that's not really going to help. So d of v is equal to cosine y dy. V is equal to sine of y. Plugging this in to our equation right here, our formula I should say right here, plugging this in, we get this. This bracket right here is only used if we have boundaries. We would place the boundaries right here. So let's say if our boundaries are 2 and 5, we would place that right here and put these into our integrated factor. Now, from here, we are just going to integrate this part. That leaves us with y sine of y plus cosine of y. The integral of sine of y is negative cosine of y, and since there's a negative on the outside, the negatives combine, which yields a positive. So we are going to keep that. This is our cosine of y times y dy. That is that completely integrated. Now we're going to look at the right hand side. We can use a red pen for that. So we're going to take this and we're simply just going to have a u sub. So we're going to be left with du over e of x is equal to d of x. Now we can substitute du over e of x into d of x. By doing this, the e of x's cancel out. So if we put d of x in here, we would have d of u over e of x, and this would become u. And the e of x's would cancel out. Rewriting this, we just get 1 over u du. Integrating this, we get ln of u Plugging back into u, we get 1 plus e of x, just like this. So that is that integrated. Now we are just going to combine these together. So when we combine them back together, this is what we get. Y sine of y plus cosine of y is equal to ln of 1 plus e to the x. Now, this is really as far as we can go. We cannot separate anything from here. However, we do need, since there are no boundaries, as we said earlier, we need to make sure there is a plus c. I always put it on the far right hand side. There only needs to be one constant c. Now our points are 0 for x and y is equal to pi over 2. I'm going to plug these in here. So now that we have that, we can see that sine of pi over 2 is 1. So this is going to be 1. Cosine of pi over 2 is 0. So this is going to be 0. This e of x to the 0th power is just going to be 1. So this is going to be ln of 2. This equals pi over 2 equals ln 2 plus c. So that means c is going to be equal to pi over 2 minus ln of 2. After we plug c back into this equation, it's going to give us our answer. So we're just going to have y sine of y plus cosine of y is equal to ln 1 plus e of x. These can turn into parentheses since e is always positive, plus pi over 2 minus ln of 2. And that is the final answer. For 14, we're asked to solve the differential equation y prime equals x minus xy in two ways. First, by using the theory of separable equations. Secondly, by using the theory of linear equations. We're going to solve the first part. After we have expanded the y prime, we can separate our equation. Factoring out the x from the x minus xy, we get x times 1 minus y. We're just going to bring this 1 minus y over here under the dy, and then integrate. After integrating both sides, we get ln 1 minus y, absolute values, equals to x squared over 2 plus c. After you derive this, you are going to get a negative ln 1 minus y in absolute values equal to x squared over 2 plus c. To finish this, we have to get y by itself. Now, what we're going to have to do is multiply both sides by e to get rid of the ln that is surrounding 1 minus y. So first what we're going to have to do is move this negative over just to make everything easier. Since it is being divided over, we're dividing by a negative 1. This is going to factor out, and we're going to have a negative x squared over 2 minus c, since it must factor. And then, since x squared over 2 plus c, or actually minus c, is going to be raised to e, this equals e x squared over 2 times e to the c. This just equals c, and we can move that constant out front. So this is just going to be c e x squared over 2. So this is what we're left with. 1 minus y is equal to negative c e negative x squared over 2. If you're confused on where the negative came from, remember it came from this negative right here. Right here. We factored it out onto the other side. All we need to do now is move this over here and move this y on this side, so the y is positive. That is your answer for the separable equation part. So we're going to start with the same equation. We're going to still use the dy dx. However, we are going to bring the xy onto this side and leave the x on the right side. So the xy is going to move to the left side, and the x is going to remain on the right side. For the theory of linear equations, we have a p and an x assigned to specific values. So on the left side is where you're going to find the p. P is anything in front of this y. So for this equation, our p is going to be x. And our q is going to be whatever's on our right. So for this equation, it's also going to be x. Now we need to find, so step 1 really, is we need to find the integrating factor. There's a formula to find this. The formula is small. It is e raised to the integral of p of x d of x. So we're going to plug our x into this p of x. X is going to go here. We're going to take that antiderivative, and we're going to be left with e raised to x squared divided by 2. Step 2 is to plug it into the integrating formula. This formula, there is a series of steps you can go through, but there's also a formula for it. So the formula, which isn't terribly hard to remember, it is y is equal to 1 over the integrating factor, which is what we found in step 1. And in parentheses next to it, we have the integral of the integrating factor times q of x times d of x plus c. We're going to plug in all of our values and see what we get. So this is what we're left with. Y is equal to 1 over e x squared divided by 2. And then inside of the parentheses, we have the integral of e x squared over 2 times x dx plus c. To solve this, we're going to need to u sub. Our u sub is going to be x squared over 2. Taking the derivative of this, we get the derivative is du is equal to x dx. Now, we can set this back into our equation. When we set this back in, remember we used u for x squared over 2, so we have to have u up here. And then x dx is equal to du, so we're just going to take out the x dx part right here and substitute it with a du, and then the plus c remains. Now we can integrate this part. So after integrating, eu is just eu. So we're going to plug back in our u, which is x squared over 2, and this is what we get. Now we can see that these two cancel out, and this is going to go under our c. So our final answer is y is equal to 1 plus c over ex squared divided by 2. You could also write this as y is equal to 1 plus c times e to the negative x squared over 2. For number 15, we're asked to solve the differential equation ty prime plus y is equal to 2t. First, we're going to expand y prime into dy dt. Now, we cannot use separable equations since this dt will multiply to this y, and we will not be able to get y by itself. So for this, we can use the linear equation, the theory of linear equation. Try to do that. Now, we are going to divide everything by t. So this is what we get. Our p of x, if we're using theory of linear equations, will be 1 over t. Our q of x will just be 2. So now that we've labeled those, we can move on to step 1 of linear, the theory of linear equations. And we can solve the interval. To do this, we're going to use e to the integral of px dx. We're actually going to change this dx to dt, since we do not have any x's and we have t's. We get e to the integral of 1 over t dt. Now, after we integrate 1 over t, we're going to get e ln of t. For this, the e and the ln can cancel out, and all we're just going to be left with is t. So t is going to be our interval of convergence. We move on to step 2, where we use our theorem we use our formula y is equal to 1 over I over x, parentheses integral ix qx plus c. Now we're just going to plug in everything that we have. So for this I of x, it's just going to be 1 over t. This I of x is also going to be 1 over, or I'm sorry, it's just going to be, this I of x is just going to be t. This q of x is going to be 2. And the c is going to just be c. After we integrate this, we're left with 1 over t times, in parentheses, 2 squared plus c. Where we get the 2 squared from is this part. We can move the 2 out. We're just left with t. We're going to, since there's a 1 up here, we have to add 1. And we're going to do n plus 1. So we are left with 2 t squared over 2, and these two canceled out, which is where we just get this t from. Completing this, we're going to be left with y is equal to t plus c times t negative 1, or c over t. For number 16, we are asked to determine whether or not the following differential equations are exact. This one's pretty fast. So what we can do is compare two parts of this equation. So if we have a dy and a dx, we can compare whatever is in front of the dx and whatever is in front of the dy. Whatever is in front of the dx is going to be labeled m and is going to be taken with the derivative in respects to y. You can remember this by the fact that whatever symbol is up here, it needs to be taken in respects to the opposite. So if we do the first one, whatever's in front of dx is labeled m, whatever's in front of dy is labeled n, and is taken with respects to dy and dx accordingly. We get that they do equal each other after we take the derivative, therefore it is an exact solution. With part b, we originally start out with dy over dx right here. To get this into the form that we need to multiply everything by dx to cancel out this dx and get a dx over here. After we take that derivative, we can see that these do in fact equal each other. For part c, we look at what's in front of dx and what's in front of dy, labeling what is in front of dx m and what is in front of dy n. Taking the derivative with respects to y for the m, and taking the derivative with respects to x for the n. After we take the derivative, we can see that these do not equal each other, therefore it is not an exact solution. Problem 17 asks us to solve the differential equations in problem 16, which are exact solutions. So if we look back at problem 16, we can see that both a and b are exact solutions. We can move both a and b here and look at them. First, we're going to look at a. So the first step to solving this, we're going to be solving for a first. And the first step is to find if they are exact or not. We've already did this, so this step is complete. Now, the second step is to find the antiderivative with either respects to x or y. For simplicity here, we're just going to choose x. So we need to find the antiderivative with respect to y. To do this, we can have y be f of x comma y, and that equals the integral of, it has to be this first part of the function because it has a dx in it, and since it has a dx in it, it can be derived with respect to y. If we were to take this one, we would have to derive it with respects to y because of this dy right here. So after we integrate this, we get a negative 2x squared y squared plus xy plus gy. Now, normally after you integrate, you'd have a c. However, the gy is going to replace the c in this case. And if you were to take the antiderivative with respect to y, this y right here would be an x. Step 3 is to find the partial derivative, and now we're going to do this with respect to y. So if you find the antiderivative with respect to x up here, you need to do the opposite and find it in respect to y down here. So this is how we write the partial derivative. We just copy whatever we got here for the antiderivative into here. So after we take the partial derivative, we get negative 4x squared y plus x plus g prime y. So to get g prime by itself, we need to set this equal to n x comma y. Rewriting this, we get this negative 4x squared y plus x plus g prime y is equal to negative 4x squared y plus x. So from here, we can cancel out the negative 4xy, x squared y. We can cancel this out. We can also cancel out the x's. That means g prime y is just going to equal 0. And if we integrate this, which is the next step, we integrate this, we get gy just equals a constant. So now that we know gy is just equaling to a constant, we can plug this back into the equation that we found online in step 2. this equation right here. So this is what we get. However, we need to move the constant c to the other side of the equal sign. Right now the equal sign is right here, it equals 0. So when we rewrite it, all we're really going to do is just change this plus to an equal sign. And the final answer is negative 2x squared y squared plus xy equals c. For part B, we need to follow similar. We actually need to follow the same steps. So first we need to check if it is exact. We've already done that in the previous problem, so it is exact. For step 2, we need to find the antiderivative, and we're going to do this again in respects to y. For step 2, we need to find the antiderivative, and we are also going to do this in respects to x. So this is how we're going to write it. The integral, we're going to write it as f of x comma y is equal to the integral of 4ex sine of y minus 3y d of x. After we integrate this, we get f of x comma y is equal to 4ex sine y minus 3yx plus gy. Now we move on to step 3, which is finding the partial derivative in respect to y. So this is how we're going to write it. Now what we need to do is set this equal to n of x comma y, just like we did in the last one. So this must equal n of x comma y, so we can find gy prime. So after we set these equal to each other, we can see that the negative 3x's can cancel out, and the 4ex cosine y can cancel out. Here we're left with g prime y is equal to 0. Now for step 4, we need to integrate. After we integrate g prime y, we're just left with gy, which is equal to a constant. Plugging this constant back in to the part we found in step 2, which is here, we can see that our answer is going to be 4e to the x sine of y minus 3yx plus c, or equal to c. So this is our answer. 4e to the x sine of y minus 3yx is equal to c. For part C, we would not be able to solve it since it is not exact, and in our first step of doing this, we check if it is exact. If it is not exact, it cannot be solved. That's it for 17. 18, we're asked to consider the differential equations in the form mxy dx plus nxy dy equal to 0 below. For each one, determine whether mxy and nxy are homogeneous functions. If they are homogeneous, state their degree. So first, we're going to look at A. And to solve for a homogeneous function, we need to use t, or any real variable that represents a number. So to solve this, we can have it written either in this mxy plus this nxy notation, or we can move all of the variables like this. We can move that to one side and have just the dy over dx. However, for now, for the way it's laid out, it's easier to solve it in the given form. So for A, we're going to put a t next to all the x's and all the y's. And then we can substitute out the t. So after rewriting this, we can factor out a t for each one. So we have one t here and one t here. These are both of the first order. And since they are of the same order, it is a first order homogeneous. Now we solve for B. So for B, we have a t squared x squared dx plus t squared x squared t y d of y, and that's equal to 0. Now let's look at the t's. So this is of the second order, right? So m of x is of the second order. Now we look at this one. We have a t squared here and we have a t here. Combining these, we get t cubed. So that means n of x comma y is of the third order. Since the degrees are different, meaning since this is of the second order and this one is of the third order, they are of different orders, meaning they are not first order. That is not homogeneous. Now we solve for C, and looking at this, we can see that this is our m, and this is our n. So after we write this, we need to find out what order it is. So since there is a t right here, m of x, comma y is first order. Now for this part, we need to see what it is. We have one t out here, and we have a t in here, and a t in here. We can actually combine these ln's to be ln t over x divided by t y. This is a rule of ln. If this was a plus, it would be t of x times t of y. But since it is a minus, it is t of x over t of y. Doing this, we can see that the t's cancel out. This would return ln of x minus ln of y, which is exactly the same as right here, which is what we started out with. Meaning that n of x is also first order, meaning this is a first order homogeneous function. Now we're going to look at d. And d is ex d of x minus ey dy is equal to 0. Now we're going to plug in our t values, and what we can do from here is really nothing. T cannot be brought down. A thought we could do is multiply everything by ln. However, we cannot have an ln with the 0 inside of it, therefore we cannot do that either. So this is its form. And since we cannot move the t's out, this is not homogeneous. And that is number 18. Number 19, we're asked to solve the differential equations in problem 18 that consist of homogeneous functions of the same degree. Is it clear which method can be used? We have to solve this. We only can solve A and C as they're the only ones with the same degree. So looking at A first, we have steps that we can use to solve this. So step 1 is that our y, we can substitute y is equal to u of x, u times x. Step 2 is that d of y over d of x is equal to x du over dx plus u. If we divide everything by d of x, we get d of y over d of x, so we can sub everything in. Subbing everything in, we get x plus u of x plus x, and in parentheses x du over dx plus u is equal to 0. Since everything has an x, we can cancel out the x's, with this right here being a 1. So we have 1 plus u plus x du over dx plus u is equal to 0. Now we need to go to step 3. Now for step 3, we need to solve the separable equation. So to make this a separable equation, this and this need to go onto this side. So we're going to subtract both sides by -1. We're going to subtract both sides by 1 and 2u. Doing this, we get x du over dx is equal to -1 plus 2u. Now we can multiply both sides by d of x, divide both sides by x, and then divide both sides by 1 plus 2u. Doing this, we get 1 over 1 plus 2u du is equal to -1 over x d of x. Now, to solve this, we must integrate. Integrating the left side, we get 1/2 ln 1 plus 2u. If you're not sure how to do this, you can make a u sub right here. Or technically, since we have u in here, you can make an a sub. Setting a is equal to 1 plus 2u, like this, you can derive this, and you get dA is equal to 2du. Divide both sides by 2, you get dA over 2 is equal to du. You plug that in, and you can see how we get to this step right here. The right side is just going to be negative ln x plus c. Now, we need to raise both sides by e to cancel out the ln's. But before we do that, this 1/2 can move in here. This negative goes in here. Doing this, we get e ln square root 1 plus 2u is equal to e ln x -1 plus c. So on the left side, the e and the ln cancels out, and that's all you have to do for that side. For the right side, if we look at this, This also equals e ln x negative 1 times e to the c. This e to the c is just c. This can be brought out front, so we have c e ln x to the negative 1. The e and the ln can cancel out, so we're just left with c times 1 over x. So after doing this, we can square both sides to get rid of that square root, then subtract both sides by 1, and then divide everything by 2. So we're left with u is equal to c over x squared minus 1 divided by 2. C getting squared. C squared is just a constant squared, so it is just a constant c. Now for step 4, we need to plug back in our y. So we need to plug in u is equal to y over x. Doing this and writing the right hand side more cleanly, we get y over x is equal to c over 2x squared minus 1/2. If we multiply both sides by x, we will get our answer. This is almost our answer. I made a mistake right here. Instead of writing 1/2, since this x is being multiplied over everything, it's actually a negative x over 2. And that is our answer. So for part C, we're going to do the same exact thing with step 1 and 2. We're going to divide everything by d of x, so we can get dy over dx right here. And then we're going to plug in all of our known values. So doing this, we get this whole equation right here. We can divide everything by x, since there is an x in front of everything. We can rewrite this as this. The way that we simplify this ln of x is a log rule. And by doing that, we can see that the x's inside cancel out. So from here, we can subtract u from this, and then we can divide both sides by this. So we get this. Now, what we can do is multiply everything by the opposite of this. So if this is flipped upside down, to cancel it out on this side and have it be on this side since they're all u's. And then multiply the right side, multiply everything by d of x over x, so we can get that on the right side. So this is what you get: ln 1 over u minus 1 plus ln 1 over u minus 1 over u du is equal to 1 over x d of x. Now, we can take the integral of both sides using step 3, which is to solve the separable equation. So now we're at part 3. How are we going to do this? Well, it is a little bit too hard. This is way too hard to integrate. So we're actually going to stop here. And instead of doing this for step 1 and 2, we're going to switch it up a little bit. So solving for it like this, we are going to plug in everything we know. So doing this way, we're going to divide everything by dy instead of dx. And then now we are going to plug everything that we know in. And this is what we get. Y, and then in parentheses, y dv over dx plus v plus vy in parentheses l vy over y parentheses minus 1. With the parenthesis around that last one equals 0. So now from here, we can cancel out all the y's. We can also see that the y's actually get canceled out here. So we're just going to be left with an ln of v. We can rewrite this again as this. Once we distribute the v inside, we have a v ln of v and then a negative v. So this positive v and this negative v can cancel out just like that. And now we can rewrite this one last time as y v ln v plus dv is equal to dx. Now we can move on to step 3, and this step 3 we can actually do. That's where we integrate both sides. So for on the left side, y is a constant, and we're going to have to use this to fully integrate it. So a, we can set that equal to v, and d of a is equal to v dv dA. Or sorry, that'll just be dv. And then b, or d of b, is going to be ln of v dv. And if we integrate that, we're going to get 1 over v. So plugging this part into here, we get y on the outside. So we have a, so a and v together is just going to be 1. And then we're going to have our minus the integral of b dA, b being 1 over v, and then dA being dv, like this, plus dv still. We still have this part right here that we didn't touch. This is also part of the integral. So really it's going to look like this. And then d of x is just going to be x. I made a mistake right here. I should not have put that bracket around there. I should have just put it around this part. So it should look like that. And now when we substitute back in, we need to plug back in for x. We're going to move on to step 4, which is to plug back in our x value, well actually our v value now, which is going to be v is equal to x over y. So we can't really do anything else here. This is really it. There's not really any other way to simplify this. So for number 20, it asks us to explain the answer to the following questions. So for part A, what is the difference between a particular solution, a family of solutions, and a general solutions? So we can list out the definition for each of them. So a particular solution is the most general form of a differential equation. Family of solutions is also a general equation that can be used to satisfy the differential equation. A general solution includes all possible solutions. These are all different. So they're all different. For B, is y equal 1 the trivial solution of the differential equation? For that, we're going to look at the definition of a trivial solution. So the definition of a trivial solution is that if the function y equals 0 is a solution on an interval, we can call this a trivial solution. Since y equals 1, it is not a trivial solution. So C asks us to suppose f of x is equal to the square root of x squared minus 1, satisfies a differential equation. Can we say f of x is equal to square root of x squared minus 1 is a solution to the differential equation? So to do this, we have f of x, and we also need the derivative of f of x. So this is the derivative of f of x. We can see that in the derivative, x has to be greater than 0. For the original function, x just has to be greater than or equal to 0. Since this is the more strict requirement, we are going to look at this, since it is the stricter requirement. So this can exist as long as everything inside of here does not equal 0. So x squared minus 1 must be greater than 0, and x squared minus 1 has to be greater than or equal to 0 here. Again, though, since this is stricter, we're going to be looking at this. So if we do this, we have x squared is greater than 1, and we have x has to be greater than 1. But since we square both sides, there's also a plus minus in front of it. So that means that we can say it is a solution, negative infinity, negative 1, negative 1, 1, and 1, infinity. So that is it for number 20, and that is it for the entire review guide.